Hey, good afternoon. Uh, yeah, sorry for the slight delay due to some issues. Welcome to round 13 live stream. Okay. Okay, I think aren't that many people yet in the stream, so I think I'll wait a bit. Okay, if someone is there, can you say hi, just so I know that there are some people here? Okay, no one's here yet, I guess. So yeah, I think I can wait for a bit more. Okay, if someone's there and you're watching and you're ready to start, please say hi so that I know that someone's watching and we can start. Most people solve problem A anyway, so that it's fine if we start immediately as soon as there's at least one person watching. Hello. Hello, UG. Okay. Sige. I think we can start. So let's start with problem A. So problem A is just, you basically want to check, do two intervals overlap. Okay, so the setup is like this. Right, you're given AB and CD. This, and you want to check, do they overlap each other? Okay, or visually, I think of it this way. Right? So how do you know if two intervals overlap or not? Okay, how do you know if two intervals overlap? So I guess the direct way is to figure out, okay, when do they overlap? Well, if I have AB and CD, then they can overlap in a few ways, right? I know they overlap if C is in the middle of A and B, or what are the other cases? I have AB, and then D is here. Okay, but I have to be careful. I want to check D minus 1, because D is not included. Right? For example, if I have a D here, and CD, if I check D, okay, is D between A and B? It is, but in this problem, we don't consider them to be overlapping. Right? Okay, so anyway, so you can do that. You can think about what are all the possible ways that they overlap. So here's one, C is between A and B, D is between A and B, or the other way around, right? A is between C and B, and B is between C and B. Right. Okay, so you can do that, but it's kind of messy actually, because you have 4 cases, and you have to think carefully about what to do in each case, and you have these endpoints like D. You have to worry about, okay, am I doing D or D minus 1? Also, well, you have to think hard. Did I actually get all the cases right? Did I get enough cases or not enough cases? Maybe some of you only did these 2 checks and got wrong answer. Well, because if you have a test case that looks like this, then C is not going to be between A and B. D is also not between A and B, but they overlap. Okay, so you can't just check one side. Okay, so you have to think hard about this, but there's a cleaner way to do it. What's the cleaner way? Instead of thinking about when do they overlap, okay, it's actually easier to think about the opposite condition. When do they not overlap? Okay, so what does it look like when they do not overlap? Well, it's always like this. You have one interval to the right of the other. Or it can be the other way around, like this. Right? And it's much easier to see that those are the only two possibilities. Right? So they don't overlap if B is smaller than C, smaller than or equal. Or B is smaller than or equal to A. Okay, I include the equal case because we also consider this to be not overlapping. Right, so that's easier to think about. So we can look at the code for that. So what do I do? Same as usual. I'm going to read the input. And then the answer is no if B is less than or equal to C or D is less than or equal to A. Otherwise, it's yes. Okay, that's problem A. Okay. If you guys have any questions, just comment anytime. I might not answer them immediately, but I'll answer them as soon as I see them. Okay, there's some delay between the live stream that I'm seeing, and yeah, there's some delay due to YouTube. So I won't instantly see your comment, but just ask if you have questions. Okay. Problem B. How do you solve problem B? Okay, so what's the setup in problem B? So this time, what do you have? You have a bunch of intervals like this, for example. And you also have like a start time and an end time. This is 7 a.m. The library opens 7 p.m. where it closes. and you're trying to figure out how many times are there in between where there are no people in the library, right? And you want to add those up. Okay, what's the simplest way of approaching this? Well, the time given to you is in number of minutes, right? So what can we do? We have 420 up to 1140. And that's actually a pretty small range. What can we do? We can sort of keep track of all the minutes of the day. So we can make a list or an array of up to size 1140. And then this list will contain like booleans where, you know, let's say for each minute in the day, is there some person in there or not? Okay, and then what do? We can process the list of people one by one. And for every person we see, well, we know that from this time up to this time, we have to set the list as person to true because there's someone in there, right? And then what will we end up with? Well, the ones where there are no people, you're gonna end up as false at the end. And we can just count those, right? So how is that going to look like? Let's write the code. First, what do we need to do? Well, we need to read the input, right? So M, and then we can have enter and leave, let's say. Like that. Actually, we don't need to save this, right? We can already put the Boolean array of times at the front. Right, so has person, let's say. And you fill this out with false, right? You can do it however way you want. So I think the simplest way is just, you can do this. I need up to 1140, so plus 1. Okay, you can also do it this way. Okay, I don't need to save the enter and exit times. I can just compute their effects as I'm reading them, right? I'm not really using them anywhere else anyway. So I can just do this. I can get the enter time and leave time. Okay, then what do I know? I know that between enter time and leave time, all of the times between those two, there's gonna be a person inside the library, at least one person. So for time in range, and I don't consider the last minute, the minute that the person leaves, to be included, right? So this is actually fine. This person, that time, is true. Okay, how do I get the answer at the end? My day starts at 4:20 and ends at 1:40. If there's no person during that time, then I know that I need to add to the total time. Okay, let's call it the total free time. It's the amount of time where the robot is free to go out because there's no people. So total free time has to increase. And I can print the total free time at the end. Okay, and we can test if it works. Okay. Okay, seems to work. Yeah. That's problem B. Okay, so I guess the more interesting problems are K and D. So let's go there now. So problem K. Okay, so actually, the scenario in problem K is basically the same as problem B. The story is just slightly different. You just want to find how many people, how many times are there during the day that there's no people in the library. how do you do that? Well, what's the difference? The difference is this time, because the times are given in seconds, the range of times is way larger. So for example, right, yeah, we can look at the start and end times in seconds, the opening and closing times in seconds, and that's this number and this number, right? Slightly bigger numbers. But if you try the same solution, it's actually not gonna work. Right? What's gonna happen? Well, it's gonna be a bit too slow. Okay, bakit? Why is it too slow? Well, what's the worst thing that can happen with our solution? Let's go back to our solution here. Okay, so this part, what's gonna happen? This part, this loop in here, how long does it take? You spend exactly leave minus enter amount of time running this loop. And then out here, you have n, right? In the worst case, what can happen? Well, the enter time and the leave time can be very far apart from each other. So in this problem, this can actually be, worst case, roughly 40,000. And what is n in this problem? N is, I believe, 300,000. Yeah. Okay, so if you take that together, then you need, this one actually runs, need to do this operation roughly. Roughly this amount, this number of times. And that's just too slow, right? We know we can only do up to 10 to the 7 operations in 1 second. So this is already like 12 times 10 to the 9. Okay, that's too big. So we need a better idea. Okay. So the people who are watching, do you guys have an idea? What can we do to make this faster? Hmm. Okay, what's actually the problem with this solution? What's wrong with it? Why is it so slow? Well, if you have some intervals like this, right? For example, you can have like these long stretches of time in the middle where actually nothing interesting is happening. Then what do I mean by nothing interesting happening? Well, when do we know what's relevant? What do we need to care about for the answer? Uh, well, we just want to know, are there zero people in the room or not, right? But during this long stretch of time, no one's coming in the library, no one's going out of the library. So actually, the number of people in the library is not changing. Okay, so why do I say it's not interesting? Because the only interesting it's only interesting when the number of people increase or decrease, right? Because that's the only time where it has some effect on our answer, right? If I have these long stretches of time that I know that exactly the same number of people are in the library, then I'm not adding anything. So this actually plus zero to the answer. During this entire stretch of time, I already know that. I don't really need to mark all of them true anymore, right? One by one. Imagine I have a lot of them. If I know that, for example, at this point, I somehow already marked that all of them entered the library. There's already four people. I already know that up to this point. And then up until this point, nothing really happens. I don't really need to do this marking to get my answer, right? Okay, same thing that happens, well, it's a bit similar to the other case where there's no people in the library. Okay, so this is when there's some number of people in the library and the number of people doesn't change. I'm not really interested in what happens in the middle at all. I don't care. The answer doesn't increase. So I'm wasting some operations by doing those one at a time. Okay, what can I do instead? Well, what's the other case? The other case is, well, you have people like this who came into the library at these times. And then you have more people there, right? And then you have, again, this long stretch of time where nothing interesting is happening. Okay, what do I mean by nothing interesting happens? Well, again, the number of people aren't changing, but it's not exactly like the previous case. Because here, this entire stretch of time, we need to like plus 1 to the answer, right? Okay, but also, like I don't uh, I don't necessarily have to check all of those one by one, right? To know that I need to add 1 to the answer. So for example, if I know that like, this is the last time there was someone in the library, and then after that, this is the first time there was someone in the library. For example, let's call this time T1. Let's call this time T2. Okay, I don't need to check all of the times from T1 to T2 one by one, right? I know that my answer has to increase by T2 minus T1. Okay, but let's handle it one at a time. So let's say I want to handle this. How do I avoid like marking every position for each person? Oh, marking all of the times from the enter time and the exit time for each person. How do I avoid that? Okay, what do we really care about? Well, we don't actually care about uh, we don't actually care about the exact times that every person enters and leaves. To get the answer, all that's important is how many people are there in the library, right? So how about this? Okay, let's imagine what's happening in the library in real life, right? What's happening? Let's say you have these people entering the library. Okay, for example, okay, so this is the start of the day. Okay, so what's gonna happen? So from this time up to this time, we know that there's 0 people. And then someone enters the library. So this guy enters the library. The number of people who entered the library increased by 1. Okay, so we know from here to here, there's 1 person. Okay, but we don't want to mark that one by one. But let's think about it. Let's keep going. Okay, what's gonna happen? As the library keeps running, people are gonna go in. You can imagine like there's a guard at the front of the library. When someone comes in, they know that the number of people who is in the library increase. When someone goes out of the library, they know that the number of people in the library decreased. Right? So, like, for example, the guard sees this person at this time. Oh, I know that there's now plus 1 person in the library. I see again this person here. Oh, there's another plus 1 in the library. and the +1, the library. And well, this person left, so the guard knows from this point on it's -1 person from the library, -1, here +1. Okay, what do we know? What does the guard know? The guard knows. The guard can actually answer how long are there, how long is the time when there's no one in the library, without keeping track of if is there a person in the library at this time or not. The guard doesn't have to like look at his watch minute by minute and check, oh, is there someone in the library? Doesn't have to keep looking inside the library. Oh, is there some person in there? Is there some person in there? It doesn't have to do that repeatedly, right? Why? Well, the guard is smart. He knows that if he sees the +1 person, +1, there's 3 people here now. At this point, there's 2 people, 1 people, 2. There's now 1 person. Okay, we're following the timeline from here to here, right? So I started with 0 people. Now it's 1 people here, 1 person here. There's 2 people here, 3 people here, 2, 1, 2, 1, 2, 1, 0. And then the guard knows between the last time there was 0 people and the next time there's at least 1 person in the library. Well, during this time, right, there's no people in the library. So the guard can actually figure out the answer without knowing at every single time is there someone in the library or not. Okay, and that's the idea for problem C. Okay. So how do we write the code for this? Well, like before, we're going to have, we can afford to make a list for all the times still, because the input is not really that big. 68400, that's fine. You can make a list of size 68400, no problem. But we're gonna change what we store in that list. Instead of storing for each time, actually, there are 2 ways to go about this. Yeah, the first one is, let's still make a list of 668,400. But instead of storing, is there someone in the library at this time or not, we somehow have to store like how many people are there in the library. Okay, and then we have to handle these events, right? So these events are going to come in. And we have to handle them. Okay, I think this is a bit easier. Don't think about this. Forget what I said about the 68,400 list for now. Okay. We just need one number. We just need to keep track of one number at any given time. Right? The guard just needs to keep at the back of his mind just one number at any given time. How many people are there in the library? Okay, so what do? We're gonna have to pick up the input and then break it down into 2 events per input, right? there's an event where the person enters and the person exits. So we collect all of those events, and then we can sort of simulate what happens as the day goes by, right? So that means we're gonna have to sort the input by time, by the time that they happen. The events, we're gonna sort them by the time they happens. When someone enters the library, we increase the number of people. When someone exits, we decrease the number of people. And then what? Well, we have to figure out the answer somehow. And we know that, so we have to think carefully about what happens when there's 0 people in the library. Okay? But that's the plan. So let's do it. Okay, so first thing I want to do is read the input like before. Then what? I'm gonna have an enter time and leave time for person I. And I want to collect those events somehow, right? So what do I do? So I'm going to say at time enter, a +1 is going to happen at that time. And then at time leave, a -1 is going to happen at that time. And I want to store that information, so let me do it this way. So now my event is going to be a list of pairs. So each pair in the list stores what time does the event happen and what happens during that event. Does the number of people increase or decrease? Okay. And then what? Well, I need to sort this list of events somehow. So you can do sort by time. Okay, and then what? I'm going to go through the list of events and simulate what happens, right? How do we do that? Well, maybe we can still like do it step by step, right? I mean, what's our bounds for this problem? We have 25,200 up to 68,400. It's not so bad, right? As long as we don't do something expensive inside this loop, doing this outer loop, doing this kind of loop, okay, it's going to be fast enough. And how do we avoid doing something expensive? Well, we're going to keep track of number of people in the library. Right, so initially it's 0. So what do? The number of people in the library is 0 at some time. Then we know we have to increase the answer. What else? Well, what do we want to do here? Well, we need to add 1 to number in library for every person who enters at time at the current time, right? So it would be nice if we had something like this. Number in library plus equals how many entered at time, right? And then some people are gonna exit, right? So we have to do like number in library, how many exited at time. Okay, so that means okay, we somehow have to construct this: how many people entered at every time, how many people exited at every time, right? How do we do that? Okay, we have to change this a bit. Okay, this idea doesn't turn out to be compatible with the thing we're thinking here. That's okay. Sometimes you do it this way. You figure out that there's an operation you need to do down here. It would be convenient to solve the problem if you did that previously. If that's not what you previously did, then change what you previously did to support that. Support what you want to do here now. Okay, so maybe this idea is still useful somewhere else, so let's keep it. Let's do something else. Okay, so what do I want to do? I want how many entered at time t and how many exited at a given time. Okay, and I know that before I've read any of the data about the n people, I know that there's 0 people entering and exiting at all times. Okay, let's add +1 to be sure. So what's gonna change here? We actually don't need this. If I know the enter time for person I, then it's easy, right? I know that the number of people who entered at time enter has to increase by 1. And then how many exited at time leave increased by 1. Okay, and if you look at it, the solution is actually fast. Why? Right, this is only O of n. This is also this is like O of 6. It's around 684 e minus 252 operations, proportional to this number of operations, or around roughly but anyway, it's manageable, right? Okay, so there are some things that are actually wrong with this solution, but I'm not going to point it out. This is already the main idea, and this is enough to solve the problem. If you're watching this and you didn't solve problem C during the contest, I suggest that you think about, you try this and you test it, think about what's wrong with the solution and figure out the fix yourself. Okay? The hint is, it has something to do with the fact that we're not considering the time that someone leaves the library. We're not considering them to be in the library during that minute, the exact time where they leave the library. So you have to think carefully about the boundaries, what's going to happen, right? Okay, and then I'll put up the complete solution later on in the website. Okay, there's something else that I want to say about this problem, which is usually you will see people, you will see some other problems where they have a similar solution to this, and usually you will see people solving them by combining these two arrays. Because, you know, if you think about it, I don't really care about the number of people entering and the number of people exiting separately. What I really care about is the change in the number of people at a given time. Right? So, change in number of people at a given time is what? Well, again, it's 0 initially. And then, well, when someone enters at that time, the change increases by 1. When someone leaves at that time, the change decreases by 1. And then down here, you don't have to care about the entry and exit separately. You just care about what's the total change. And right, the change can be negative, right? Because if there are so many people going out at the same time, then the change is negative. Okay. So this is what people usually call a difference array. You can look for this in Google later on if you're interested. So the idea is, instead of storing what's the actual list that you want to maintain, because we have an actual list that we want to maintain, right? The actual list we really wanted to maintain at this point is real array is number of people in library, number in library, right? So you can imagine we change the solution a bit, right? Instead of just keeping track, what's the number of people in the library right now? We can also compute what's the number of people in the library at all of the times, right? We can do that. It's not important for this problem, but we can do that. And then we can say, like, okay, like this, right? At the current time, if the number of people in the library at the current time is 0, then we have to do something. Increase our answer in this case. Otherwise, well, it's the number of people in the library at the previous time plus the change that happened now. Okay, so the real array that we want to keep track is really this number in library. It's the thing that we care about really to get the answer. Okay, but sometimes maintaining this number in library, this real array that we want to maintain, is expensive because we have to add. We were given ranges of updates this array. We want to add 1 to everyone in this, to every number, to every index within the range, or we want to subtract 1 to every index in the range. That's going to be slow. The trick is, instead of looking at the real array, you look at the difference array. Difference array is just what's the difference that happens at every time. And this difference array helps you for those types of problems where you want to maintain some real array, and on that real array, you're gonna do range, what we call range updates. We want to increase all the indices within this range, the values within this indices, by some number. Okay, that's exactly the setup we have in this problem. Right. We have something like this, and we want to increase. This is our entire array. We want to increase the value within this range, and then increase within this range. Okay. So anyway, you can go look for that later if you're interested. Okay, there's one more thing I want to say. Again, this solution is actually not exactly right. There's something wrong with this solution. And again, that's related to the fact that you have to think carefully about what happens at the boundaries. Do I actually decrease at this time, or time minus 1, or time plus 1? And here, do I want to apply the change now before I check if it's 0, or apply the change after I check if it's 0 or something? Okay, but you can think about the details. It's related to why the first one is wrong. Okay, so if you're watching this and you haven't solved problem C, I recommend that you use the idea that I introduced here. Try to solve the problem yourself first, with the full details, and then I'll show the complete code later on in the website. Okay, there's one more thing I want to say about this problem, which is actually this idea is useful and will solve an even harder version of this problem. Right? So let's go back to it. Okay, let's change the problem a little bit. So that instead of having from time 25,000 to 68,000, the times are now, let's say, let's go here. So in this problem, we had, right, time is between like 20,000 and 60,000, 70,000, right? So that's a small amount of time. And we can fit all of the individual units of time in a list. And we can get the answer. We can actually say how many people are there in the library at every single point in time. Because we're only going through a small range of time. Right? But let's change the problem a bit. Let's say that the times are now up to 10 to the 9, or maybe even up to 10 to the 18. Okay, then you can't do what we did anymore. You can't just say, let me construct a list of size 10 to the 9 or 10 to the 18. That's going to be too big. So what do you do there? So you can't do this. You can't say like 10 to the 18. Okay, that's just too big. But, well, again, you can use this idea of there's nothing interesting happening in most of those times anyway. The interesting events happen when people enter and when people exit. So again, you can sort of do something with this idea, right? You can go through each event. And then keep track of what is changing at every time, and also keep track of how many people are there in the library still, right? And this time, when there's no one in the library, instead of adding 1, well, you need to know what the previous time was, right? So you have some kind of previous time. So something like this is the idea, right? So there's no need to look at all of the individual time steps. You can just look at the interesting events that happen. Okay, so for those of you who've solved problem C but haven't done this kind of trick before, I recommend you to try this kind of solution. And again, I'll post. This isn't complete. There's lots of details that I'm skipping here because I want you guys to think about it. But you can look at it later. I'm going to post the full code in the website. Okay. All right. So before we move on to problem D, I have to take a short, important break. So give me a minute. Okay, so that's problem is problem D. How do we do problem D? Okay, so what is the problem about problem B? So this time, what do we want to do? So there's a bunch of people who want to borrow the book, and they want to borrow the book between several times, right? So, for example, person A wants to borrow the book this time. Person B wants to borrow the book this time. C during this time. And then you could have overlaps, like person D wants to borrow the book at this time. Person E wants to borrow the book at this time. So, one possible solution is you let persons D and E borrow the book, but that's not the best solution, right? The better solution is you let 3 people, A, B, C, borrow the book. And the problem is, how do you figure this out? Right? So definitely you can't like let person A and person D both borrow the book, because their times are overlapping. So what do we want is we want the maximum. Take the maximum number of intervals so that no two overlap. Okay, so what can we do here? Okay, so if you thought about this problem, maybe you have some ideas. Like maybe I can prioritize the people who want to borrow the book for the shortest amount of time, right? Right, because that's gonna free up the book for more people if people only borrow for a short amount of time. So prioritize shortest time first. So if you think about it, how do we implement the solution? Well, we're gonna sort the input somehow, and it's gonna use a custom comparison function because we want to sort by some custom rule. We're gonna sort the people by the amount of time they want to borrow the book. So this is doable. And then what do we do? Well, we just process the people one by one. And then if the new person that we're looking at, right, so we're going to process them one by one, right? So maybe I got the short guys first. And then I get a new one, like this. If it overlaps with some of the intervals I've already chosen, then I can't pick that, right? I just throw it away. Okay? Otherwise, I keep going. Like, for example, if I get something like this, that's fine. And then I get something like this. Oh, it already overlaps, so I don't include that. Okay, so we can write a sort of solution that works with that idea. What does it look like? So we can do this. So we can say, okay, first let's read the input, and then each person has enter time, leave time, and also what? Yeah, let's read it. Enter time and leave time. But also, aside from just the enter time and the leave time, well, we want to keep track of the index later, right? Because we want to print out the exact list of people that we lent the book to. So let's have the index. And because we're indexing starting by 1, then let's add 1. Okay, then what? Well, we can sort the list of persons. And I've talked about this in a previous video. How do you introduce a custom sorting rule? So we can do it this way. We sort the list of people by smallest amount of time they want to borrow the book to largest amount of time. And how much time is the person going to borrow the book? Well, we can extract the info from the person again. And then the amount of time that the person is going to borrow the book is just leave minus enter. Right? Okay, I use leave minus enter because that's what we did in the previous problems. You can find the more descriptive names for this problem if you like, but that's not really important. Right? Okay, and then you can do this. Persons chosen. Initially, there's no one. And then we can go through all the people. Right? And then we can choose this person only if there's no one that it overlaps with. So let's do this. Okay, maybe this is the easier way to do it. Okay, if compatible, if not compatible, so we keep track of, we need to check, can I add this new person in the list of persons chosen, right? So I need to check now, is this person compatible with all of the other people I've chosen so far? Is this new? Yeah. So enter, leave, other, enter. And only if it's compatible with everyone, then that means I can add. add this new person. And then you guys know how to print. And how do you do this compatible check? Well, that's exactly problem A, right? So we don't have to do that again. You can simplify this a little bit. This is actually Python magic. You can do like if all compatible. So if it's all compatible, then you can add this new person. Okay, and that's one possible solution. The question is it right? And so do you think it's right? Okay. Well, if you thought it was right, then you're wrong. It's actually wrong. Here's an example that shows why. Let me see if I can draw a nicer example. Okay, I think this example makes it very clear why it's wrong. I just have 3 intervals like this. Well, if I prioritize the shortest one, I'm going to take this guy. Right? But that's not the optimal solution. The optimal solution is to take these 2 guys, even though they're longer. Okay? So the issue is somehow the shorter is not always better kasi it's possible that the shorter interval has more conflicts, right? So this one has 2 conflicts, or there's 2 intervals that are incompatible with it. These guys have only 1 conflict each. So in this particular case, would have been better to prioritize the one with fewer conflicts first. Right, so maybe that's the correct answer. Right, so you can modify the code that we did here. Instead of sorting by amount of time they want to borrow, you define like a different function, number of conflicts, right? And you can figure out how to compute that. Okay, but even if you do, well, actually before you do, it's always useful to think, is it actually right? Is sorting by the prioritizing people by the number of conflicts the right thing to do? And you have to think about this first, because if you don't, you probably waste some time writing the code and then it turns out it doesn't work, right? So here's the thing with what we call greedy algorithms. So yes, if you have a greedy algorithm, then it's probably easy to guess some kind of greedy. Why do we call it greedy? Because you're like prioritizing according to some single criteria, and you're being greedy on prioritizing on that. So yeah. What's the problem with the greedy algorithm? Well, it's very tempting to just throw a greedy algorithm at a problem, because you can easily come up with a greedy algorithm. And when you hear a greedy algorithm, or you come up with a greedy algorithm yourself, you think about it, it feels right. It feels intuitive and it feels right. Right? So for example, itong shortest, prioritized by the shortest interval. The first time you hear it, feels right, right? So it's tempting to think that that's the correct solution, until you see this counterexample. Right? So that's the problem. Okay, something will feel right, but it's actually wrong. And you won't find out until you've wasted time or you've actually seen the example that shows you why it's wrong. So you have to be a bit careful about throwing greedy algorithms at problems. Okay, so you have to doubt yourself a little bit more from now on. If you've reached this point, you've reached a level where you can solve ABaKoDa level D problems. You have to doubt yourself a bit more from now on. Some obviously correct solutions turn out to be wrong, like this one. So we need to be careful now. Let's think first, is the fewest conflicts solution actually right? Okay, it's a little bit hard to come up with an example for this, so let me just show you. Okay, so what's going to happen? Let's look at this example. What's going to happen here? These guys are going to have a lot of conflicts with each other and with these guys, right? And with these guys. Same here. These guys are going to have lots of conflicts with each other and with these two guys. And then this one will get prioritized because it actually has the fewest conflicts. But what happens if you pick this guy? Well, you can pick at most 3 intervals now, because you pick this guy. Well, you have to pick, like, you can't pick these anymore. You have to pick at most one of these guys, or at most one of these guys, right? So if you do that, the answer is 3. But what's the optimal solution here? Well, the optimal solution is to pick these 4 guys. And even though they have the largest number of conflicts, it's okay. Wait, so it seems like we're stuck. What other ideas can we have? What's wrong with the fewest conflict solution? well, we kind of ignored the information about when are people borrowing stuff, right? We ignored too much information about the problem. We're just looking at conflicts now. We didn't even care about the length of time that people are borrowing. When did they borrow it, start borrowing it? When do they finish borrowing it? We threw that all away. But maybe that's actually the important information. Okay, so what's next? Well, here's an idea. Maybe you can try earliest start time first. So prioritize the one who borrows earlier. That kind of makes sense, right? Because if someone borrows earlier, then you have more time later to lend the book to more people later on, because someone already borrowed it now. Okay, so think about it for a minute. You can actually pause the video if you want. I encourage you to pause the video and think about, if you're not watching this live, you can pause the video and think about, is this actually right or not? Okay, so is it right or not? Well, if you thought it was right, then you're wrong. It's actually wrong. Here's the example. Right, so what's going to happen? You're going to prioritize this guy, and then you can't pick any of those anymore. But the actual solution is actually to pick all four of those, right? Okay, so still not right, because yeah, if you sort by earliest time, then it doesn't take into account the length of time that someone borrows the book. Okay, so it feels like we're kind of stuck, right? Because each of these rules have something missing to them. If you sort by shortest time first, doesn't take into account the conflicts. If you take into account the conflicts, doesn't take into account the times. And if you sort by time only, doesn't take into account the lengths of the times. So each one has their own weakness. So now what? Do we give up? Well, one thing you can do at this point, if you're experienced already, is you can do dynamic programming itself instead. Dynamic programming. And if you know how to do this and how to reconstruct the set of people you're supposed to choose from the dynamic programming solution, you can actually solve this problem with dynamic programming. It's a little bit more complicated than needed, but it solves the problem. And the bounds are small enough for this solution to work. But well, if I gave you a different version of the problem with slightly larger n, then this isn't going to work anymore. And also, this is a bit harder to code than a greedy solution, which might be simpler. Okay, so there's actually a greedy solution here for this problem that does work. So the greedy solution that works is like this. you can sort by prioritize earliest finish time first. Okay. And this actually works. And if you try a bunch of test cases, it's going to work. You compare the output of a solution like this with the brute force solution or a DP solution, it will get the correct answer almost every time. Actually, every time. And you try 1,000 test cases, 2,000 test cases, 10,000 test cases. Seems like it's correct, and you might believe it's correct. Is it actually correct? What if there's one test case that you missed somehow? Like, for example, here, like it sounded right, and if you test it a bunch of test cases, it will actually do the right thing. Same with this solution, same with this solution, but all of them have this small test case that they will fail at. Won't that happen here? Maybe you just didn't try hard enough to find a counterexample. Maybe this is actually wrong. Okay, so testing is not enough to figure out if a program is correct or not. So this will sound weird the first time you hear it, but this is actually a thing. We prove solutions correct or not, right? We prove that programs work or not. It's a thing that we do. Okay, because once we have a proof, then we're gonna be 100% sure that the program is right, and we don't rely on just test cases. And we know it's correct, and we don't have to worry about, oh, maybe there's a test case that doesn't work, because we've already proved it's always correct. Now, how do you prove that the solution is like this is correct? Or how do you even prove that greedy solutions are correct in general? So the idea is you make an exchange argument. So what is an exchange argument? Well, let's pretend that you have some other solution that is not the same as your greedy solution. So this is my greedy solution. And then there's some other solution. And you're saying because greedy solution is not, you're gonna try to somehow like assume that there's another solution out there that's not my greedy solution, and that was actually the right one. I was wrong, the greedy is wrong, that was actually the right one. Assume optimal. And then here's what we're gonna do. We're gonna slowly exchange the greedy solution. We're gonna slowly modify the greedy solution so that it looks more and more like that other solution that we said was optimal. If at every step that we do this, every single exchange that we do, the number of people that we can serve does not decrease. What does that say? Well, it means we started with an optimal solution all along. The greedy solution was optimal all along. Because we can always exchange, keep on exchanging, keep on doing these exchanges without changing the quality of the solution and make it more and more like an optimal solution. Okay, sorry, I think I said that in the other way around. We have to start with this solution that we said was optimal. And then we slowly make changes to that optimal solution so that it looks more and more like the greedy solution, right? If at every step we didn't make the solution worse, then it means that the greedy is actually the best solution, or one of the best solutions, right? You can think about it this way, right? Here's the landscape of all possible solutions, and here's the number of people. And the x-axis represents like some way to encode the solution numerically. It is not important. Let's just say you found a way to map each solution to a single integer and you graph it. So maybe the space of solutions look like this. Right? There are going to be some solutions where you cannot serve that many people, and then this is the optimal. Right? So what I'm saying is, how do you know that this is the greediest up here? Well, you start with some random solution. Use a different color. You start with some random solution out there that is not the same as your greedy, and you transform it bit by bit so that it looks like your greedy solution. And if you know that you started with a random solution, right? It could have been this guy. It could have been this guy instead, right? Or this guy over here, or someone else, right? If at every step in transforming the solution to the greedy one, you always only made it better, then you know that the greedy one is on the top, right? And you didn't pick any specific starting point. If at all starting points, regardless of where you start, you just keep going up as you transform it to the greedy solution. The greedy solution has to be the best one, because from anywhere, you start from anywhere, you keep going up, and you reach greedy, then the greedy is at the top. So that's the idea. So how do we think about the problem in that way? So let's pretend that I have an assumed optimal solution that is not the same as my greedy. And here's my greedy solution. Okay, what's going to happen? Okay, since this assumed optimal solution is not the same as the greedy solution, then there's going to be one choice that they didn't do quite the same. So for example, maybe this first guy is the same, the second guy is the same, the third guy is the same. Okay, but maybe this fourth guy is not the same, right? I did something else different in the optimal solution, and then in the greedy solution, I picked someone else. Okay, we're assuming we're looking at the intervals that both solutions took in increasing order. Right? So what's going to happen? Well, there's one thing we do know, because we prioritized by earliest finish time. Well, what's going to happen? What do we know? Well, we know that this finish time has to be smaller than that finish time. Right? Because that's what the algorithm did. It picked the earliest finish time. Okay? Okay, then what do we do? Well, there's some other intervals there that we didn't consider yet. Maybe they're the same still, maybe they're different, but there's some other intervals there. But what happens? If I exchange this optimal solution, the choice that was made by this optimal solution, with this choice that was made by the greedy solution, then I can still pick all of those guys, no problem. Right? I exchange this with this, then no problem. If my answer previously for this solution, my answer was X, after doing one exchange like this, it's still gonna be X. Possibly even larger, because maybe there's another interval here that I didn't consider, that I couldn't consider because I picked this purple interval. But now, after I exchange it, I now can suddenly pick more guys, right? So if my answer was X before, it's either still X or even better or greater than X. So I've just argued that if you start with some random solution that you think is optimal but it's not the same as the greedy one, and you slowly transform that into the greedy solution, you will always just keep increasing the answer, or it stays the same. And that means the this greedy rule is optimal. Okay, so yes, greedy is not going to be wrong all the time. There are some greedy solutions that do work, but you have to think carefully about why do they work. And one technique that you can use to prove why greedy solutions work is this exchange argument. Like, start with some random solution that you believe is optimal, slowly transform that to a greedy solution, and if the answer just keeps getting better as you do the transformations, then the greedy solution was one of the best solutions to start with. Okay, and I guess it's not so hard to write the code for this one anymore. You've seen the template earlier. It's just a small modification to that code to implement this idea. Okay, but that's problem B. Okay, so the lesson is, don't be greedy. Greedy sounds right, but is often wrong. The second lesson is, sometimes greedy is right, but you have to prove that it's right. And the way you prove it is, one of the ways to prove it is use exchange argument. Okay, that's it for this stream. I hope you guys learned a lot from this stream. I hope you guys enjoyed today's contest. And see you guys again next time.